Okay, this will be lecture 15. And we're going to do the first half of chapter 9, 9.1 and 9.2. It's about hypothesis testing. The last part of the class, chapter 9 and chapter 10, what we do cover is hypothesis testing. And yes, it's very popular, and yes, it's all over the finals, so definitely get into it. It's a step-by-step process, and it's not all that bad, so let's give it a try. I think I picked out some better examples for you. Hypothesis tests in general, and then we'll talk about the mean. There's a couple of different cases about the mean. One, if you know sigma, so you're able to use z. One another, when you don't know sigma, all you have is s, and then you must use t, as we've gone through before. And here's an opening example. Would you graduate from college with debt? Many people do. If yes, how much money do you think you'd owe? And did you know that students who graduated from public and nonprofit colleges back 7 years ago with loans had an average debt of $28,400? And it varied a great deal from state to state. New Hampshire had a pretty high one, and New Mexico was considerably lower, probably reflecting the cost of living in each state. So we have an introduction to hypothesis tests. We'll have the two hypotheses. We'll have what's called a rejection and non-rejection region, two types of errors and various tails of a test that kind of categorize everything. So we have two types of hypotheses as we set up hypothesis testing. The null hypothesis is a claim about a parameter, typically something like the mean, and it's assumed to be true until it's declared false. The null hypothesis is H sub O, or HO, or H0, whatever you'd like to say. Alternative hypothesis, in this book it's H1, other books it's HA. I will take either one of those. But the alternative is the thing that comes up and challenges the status quo known as HO. It's a claim about a population parameter such as the mean, or maybe the proportion. That would be declared true if the null hypothesis is declared to be false. So it's kind of the winner by default. And we have some ideas from our book. For in the rejection region, let's just start with this one first. If we reject HO, because it's an HO world that statisticians live in, we have found enough evidence to declare a person guilty in a jury trial, and hence the null hypothesis is rejected in this region. And if he's in a non-rejection region, the person would have not enough evidence against them to be declared guilty. And hence the null hypothesis is not rejected, and so we do not reject HO, and then the person is not considered innocent, they're just considered not guilty. So there's a difference. So rejection versus non-rejection is always considering HO. We'll talk about the preferred hypotheses later, which sometimes is a more direct way to get to it instead of getting into triple negatives, as could happen. Okay, the book also continues a little bit longer. If the court's decision is that the person is not guilty in a jury trial of whatever it may be, anywhere from jaywalking to mass murder, we don't know, but there's a court that's deciding on this person's guilt or innocence. And so the actual situation, when they say the person's not guilty and the person's not guilty, that's exactly what we want to see. That's the correct decision. If, however, the court's decision that the person is guilty when the person is not guilty, that's bad. This is a type 1 error. It's also known as alpha. We've actually looked at alpha already. That's the one we spend a little time with, is the type 1 error. So this person is the innocent person going to jail. Now, how do we know the actual situation? Well, it's a hypothetical situation. Let's take a look at the other kind of situation when the person is found, perhaps with DNA evidence decades later or something like this. The person is found to be guilty much later on, and the court decided that the person was guilty. That would be a correct decision. Guilty person going to jail, or whatever the sentence may be. And so that's fine, but there's the other type, where the court's decision is that the person is not guilty, but the person really is guilty. This is a type 2 error. So this is the guilty person going free, guilty and free. They don't like this. It's also called beta. We're not going to spend any time with beta. It's just there as a reference. We're going to just kind of slide past it. It gets pretty heavy statistics-wise, so we're not going to really spend much time with beta. The type 1 error that we do spend a little bit more time is with the type where this is the really sad case where the person turned out to be innocent, but they're going to jail or worse. So that's the type 1 error. Two typical kinds of errors. Well, we'll talk about them coming up in more of a real-world situation. Okay, so looking at another set of examples, a process that uses sample statistics such as X bar to test a claim about the value of a population parameter such as the mean is a hypothesis test. For example, consider a manufacturer that advertises his new hybrid car and they say it has a mean gas mileage of 50 miles per gallon. But if you suspect it's not 50 miles a gallon, how could you show that this advertisement is false? That's something we'll let you get to in a bit. Statistical hypothesis is a statement about a population parameter, and we carefully state a pair of hypotheses, one that represents the claim and the other the complement. Now, sometimes we see problems that don't have claims per se. I'm not one that really inflicts that on you so much, but if it's clearly stated, then it sure doesn't hurt to talk about it. And it's just another way to frame the answer. And you could say that not only do you reject the null hypothesis, but you reject the claim as well, things like that. But because we seem to always get to this material towards the end of the quarter or semester, I don't really force that on you. I just say, look at the hypotheses and make your decision based on that. But most of the time, there's a claim that's written down that goes with it. Some books are all over it, others aren't. When one of these hypotheses is false, the other must be true, and that's the way I like to look at it. And either hypothesis, the null hypothesis or the alternative hypothesis, could represent the original claim. It seems like mostly the claim goes in the alternative hypothesis, but that certainly isn't always true. And so a null hypothesis, HO, is a hypothesis that contains a statement of equality. And the one that I focus on the most is the equal sign. However, you may also run into, especially on web work, greater than or equal to or less than or equal to. But the main one is equal. And as long as you're talking HO, the way I teach it is you can always put the equal sign in the HO statement and not worry about it. All the important information goes in HA anyway. And here's HA. It's the complement of the null hypothesis. It's the opposite, so to speak. It's the statement that must be true if HO is false, and it contains a statement of inequality. And this must be followed, such as less than, greater than, or not equal to. And these are quite important because HA has all the information in it. And HO is kind of this background double check, if you will. You can make it fancier by dressing up this and this, but I don't usually pay much attention to it. I go for the equal sign every time. That's the way most books nowadays are teaching it, but I have a couple of examples that are not quite doing that all the time, although your book does do the equals a lot. And H sub 0, H sub A, H sub 1. So notice how different sources have different H's, but HO is always HO, no doubt about it. And with the alternative, you can say either HA or H1. That's up to you. Our book does use H1, however. I just found this set of examples to be a little bit more readable than our book, no offense. That's why I'm using it. So to write these hypotheses, translate the claim made about the population from a verbal statement to a mathematical statement, then write its complement. And so we'd have HO, something to do with K, and so we have all these possibilities. Let's use the mean equal to K, and maybe the mean is less than or equal to K. Notice how HO is the same thing every time. That's the way I teach it, and that's just fine with me. It takes a little bit more pressure off of you. But looking at HA or H1, that's where the information is. The challenge to this is less than. The challenge to this is greater than. And of course, the challenge here is that it's not equal to, which is really either one, too big or too small, kind of like a pendulum swinging too far. Regardless of which pair of hypotheses you use, you always assume that mu equals k and examine the sampling distribution on the basis of this assumption. So we kind of start off with that. And here we have a few other hints that might be especially good for you with web work or perhaps some of the word problems. I plan to make it a little bit more clear cut on the tests and quizzes, and that I'll always start off with HO equaling mu, or perhaps P equaling some constant number k. And here, of course, we already have the equal sign on the third case down here. Well, anyway, you can take a look at this. I think you'll also find it in the book. And so the thing is, the HO has to have the equal sign in it somewhere, at least as greater than or equal to. These are exactly the same thing. Some of you didn't know that on the test, by the way. I find that hard to believe, but I used to remember when nobody would miss that. Now several people, especially on 165, don't know what at least means. So be sure you know that on the final. But it's plenty of time to get that down. Not less than k, I don't use that. Not shorter than k, I don't use any of those. Less than or equal to k, sure. That's why I scribbled out. And all those other things, sort of thing, that you could just replace by the equal sign. But what would be important is H1 or HA, where less than, below, fewer, shorter. That's what the challenge is doing. And that's what we focus on. All this stuff is what matters. And then it turns out when you have equal versus not equal, it's actually pretty easy, because there's so many ways you can say equal to k, exactly the same as not changed from. Yeah, that's pretty easy. And then not equal to, different. Different's a very important word. It sends it off in two different directions. Okay, stating the null and alternative hypotheses. Write each claim as a math sentence. State the null and alternative hypotheses, and identify which represents the claim if you choose to do that. So the school publicizes that the proportion, because we can do proportion too, of its students who are involved in at least one extracurricular activity is 61%. So the solution is that P equals 0.61. Notice we should always use a decimal for calculator purposes, which you will be using. So there's no point in saying 61%, although if you happen to say P equals 61% with the HO, I'm not going to charge you for it, but since you're using your calculator anyway, you may as well ease on into the decimals. And it said at least one, so let's see how they handled the complement of that. That would be less than 61%. Now this is already kind of difficult. I would just simply say this felt that is less than 61%. That's what I would do. I would just go directly to what you want for HA. Sometimes we even list HO and HA for you, or H1 for you. But we'll make it more direct so you won't have to worry about sifting through all this other stuff. The car dealership now announces that the mean time for an oil change is less than 15 minutes. So the solution would be that the mean is equal to 15 minutes, but less than 15 minutes is direct. And it looks like the claim, which is what I'm used to, working as a associate statistician for the U.S. Forest Service in UC Riverside for a few years. The claim typically was with the alternative, whether you call it H1 or HA, that's your choice. We do not care. But we'd have the status quo kind of presented in the beginning, and then some sort of challenge to it, whether it's less, greater, or not equal to. And that's typically what the claim was most of the time. So the less than, for the more advanced point of view, does not have an equal sign. It must go in HA. Here's a third one. The company advertises that the mean life of its furnaces is more than 18 years. Well, that's got to be HA as well. So let's see how this gets worked out. We've got the mean equals 18. Let's just make it equals. You could make it harder if you want, but then you're almost asking me to take points off, and I'm afraid I have to oblige, and I don't want to. So I'm trying to tell you things that are shortcuts. Many of you did not use the shortcut on number 2 on the test, by the way. So when I tell you it's a shortcut, I'm not kidding. It is a shortcut. Save some time. You'll have more time to do the rest of the test. So here, same thing here. If you stew in your juices for 5 minutes figuring out what is HO, you've been wasting your time, plain and simple. Just say equals, and then put the other one, which does not include an equal sign, in HA. Okay, this is a number line situation, and that's no big deal. Here we have one that, technically speaking, if it was exactly 61%, HO would be the winner, and HA would get everything else. Turns out that's not really the case. What they're going to do is they're going to fan it out like a confidence interval. In fact, there's a definite overlap with confidence intervals when it comes to two-tailed tests, which we'll get to in a minute. However, when it comes to other types of hypotheses, well, we'll find that they kind of carve out one side or the other of the number line. And typically there's like a curve that's going to be overlaid on that if you'd like. I do not need sketches for confidence intervals. They're all pretty much the same, so we're not going to do that so much. But anyway, we'll talk about that later. If I get more details than that, I'll get to you. No matter what hypothesis represents the claim, and usually it's H1, always begin with the hypothesis of test assuming that the equality in the null hypothesis is true. So we assume that the null hypothesis is true, and then we seek to challenge that, maybe. Unless you're a company man, then you're hoping no challenge will be enough. But, so when you perform hypothesis tests, one of two decisions will be made. You reject the null hypothesis, or you fail to reject the null hypothesis. If you want to say it a little faster, you could say don't reject. I know it's a double negative, and double negatives mean stuff here. That's, if you don't reject HO, let's just talk about preferences. And you can certainly answer it in terms of what you prefer. Here you prefer HO in the second case because you're not rejecting it. You're not exactly accepting it. You're not exactly calling the person innocent, innocent. You're saying not enough evidence to prove guilt. There is a difference. We don't make a huge deal out of it here, but there is a difference. So you really shouldn't say accept HO. You're saying prefer HO. So then you reject the null hypothesis. Well, if you're rejecting HO, then you got to pick H1 or HA if you prefer. So prefer H1 because you rejected the null hypothesis HO, and so you're preferring H1. It's one choice or the other. And I found over the years as teaching this class, if I just get students to say, which one do you like? And then hopefully you can tell me why. That's much more effective than getting into the triple negatives. And fortunately, we're staying away from the verbose language that other books love to go for. I have a cousin who's a lawyer, and he's all into that kind of thing. Quadruple negatives and things that are kind of difficult to read. Your decision is based on a sample. There's always the possibility of making the wrong decision. Sorry, I scribbled over that. But there's always that chance. This is not a perfect science. And so here's another kind of a truth table here. So if you reject HO, that means you prefer HA, H1. So I'll just put it in terms of prefer. If you don't reject HO, you kind of like HO. You're not rejecting it. So if HO is true, you win. If HO is true and you rejected it, picking H1 instead, that's an error. That's the type 1 error known as alpha. That's the one we actually measure, or is often given to you, assumed to be that kind of a limit of alpha. So if HO is false, turns out H1 really is true. I'll just say that side by side because it's the same statement. If H1 is true and you picked HO, over on the far left, that's an error. That's known as beta. We're not going to be measuring that. And if H1 was true and you rejected HO and chose H1 as your preference, that is your correct decision. So that's just another way of sizing up your decision versus what actually is true, such as if golden tablets came out of the sky with the answer on them. It doesn't happen in too many situations, maybe in certain classic movies, but that's about it. Anyway, we can see this again. Null hypothesis rejected when it is true for the type 1 error. The type 2 error when the null hypothesis is not rejected when it's false. So you should have rejected it, but you didn't. Okay, here are some interesting ideas, and let's see if I can get that. Can't seem to get that slide off the deal. Okay, anyway, example, identifying type 1 and type 2 errors. The USDA limit for salmonella contamination for ground beef is 7.5. There's some sort of unit that goes with that. I don't remember what that is. A meat inspector reports that the ground beef produced by a company exceeds the limit. You perform a hypothesis test to determine whether the meat inspector's claim is true. When will a type 1 error occur? When will a type 2 error occur? And which one is more serious? There is one that is more serious. For example, in a jury trial, it's usually felt by most people that letting a few guilty people go free is better than having even one person in jail or even executed and when they were innocent, that's considered to be the most horrific thing that could happen. And to let a few people go free to kind of guarantee that doesn't happen, or at least to assure ourselves a little bit better that doesn't happen as much, is considered a good thing. So anyway, let's just see how this turns out for us. And solution, identifying the type. Okay, I can't see it. There we go. Finally goes away. So identifying the type 1, type 2 errors. Let P represent the proportion. So we don't always do means. We do proportions sometimes too of the ground beef that's contaminated. So we have hypotheses about the hypothesis being either equal to or maybe less than or equal to. You could even say that if you want to, if it helps you. But the main one is that we think maybe it's just a little bit too much, and that might not be a good thing. So if the ground beef meets the limits, that means P is less than or equal to 0.075. But if it exceeds, which is a bad thing, P is greater than that number. So, yeah, in this particular example, the less than or equal to might help a little bit. Let's see about how we could go along with this one. Now, when we had the hypotheses, which we had equal to, less than or equal to if you want, versus greater than, which is the main one. A type 1 error is rejecting HO when it is true. And so the actual proportion of contaminated ground beef is less than or equal to 0.075, but you rejected HO. That is a mistake. Doesn't seem quite so bad. But type 2 error is failing to reject, basically accepting or preferring HO when it's false. So the actual proportion of contaminated ground beef is greater than that number, but you do not reject it. That does sound worse. I believe they do summarize this up a little bit more. With the type 1 error, you might create a health scare and hurt the sales of ground beef producers who are actually meeting the USDA limits. So the health scare is not very good, and it hurts sales and drive the prices up and all that kind of thing, which is not very nice. But what about type 2 error? You could be allowing ground beef that exceeds the contamination limit to be sold to consumers. That doesn't sound good at all. It is more serious, that type 2 error, because it could result in sickness or even death. So just have to size these things up. Neither one are very good, but anyway, that's the way it turns out. Now, the level of significance, your maximum allowable probability. Okay, I'm going to change the color here back to another color. Very good. Of making a type 1 error. This is going to be alpha, denoted by alpha. It's also known as the level of significance. So it's the same as a type 1 error. It's a nice coincidence that works out well. And that's kind of like the probability of making a mistake that's allowable. And typical values are 0.05, the major one, 0.01 where you want to be extra strict, or if you're a little bit looser on it, 0.10. And these kind of go along with the confidence levels that we had before. Remember, this went with a 95%er, 99%er, and 90%. So very similar. It's just kind of inside out. It's almost like the complement of a confidence interval. You could say it that way. So by setting this, the level of significance at a small value, such as 0.01, you're saying that you want the probability of rejecting a true or null hypothesis to be small. So we're being very strict about it. We don't want to make mistakes. And as we said, those are the commonly used levels. The probability of a type 2 error is denoted by beta. And I guess the words I have to say about that is it's always better to have large N, because if you have a large sample size, it tends to bring both alpha and beta down at the same time. Otherwise, if you decrease alpha, beta goes up. If you decrease beta, alpha goes up. It's kind of like you can't get them both down unless you get a huge sample size. And sometimes that's just not in the cards. But that's all I'm going to say about beta. Also, 1 minus beta is the power of the test, but we're not really covering that. Anyway, after stating the two hypotheses and specifying alpha, the level of significance, a random sample is taken from the population and sample stats are calculated. And the statistic that compares with the parameter in the null hypothesis is called the test statistic. With the assumption that the null hypothesis is true, this is then converted to a standardized test statistic. And the ones we will see again are Z and T. There's another one called chi-square. We just don't have time to cover it. I've covered it in many a semester class, and I've even covered it in 262, and we were going a lot faster than we do now. But I was just following orders, and we were going more than 2 sections per day every day. It was pretty fast. Standardized statistic is used in making the decision about the null hypothesis. And here are some that we've seen. Do not worry about the sections. So I'll just change these over to chapter 9, different edition. If we're estimating the mean, the mu, then we use x bar to estimate the mu, and we'll be using z if sigma is known, 9.2, using t if sigma is unknown, in 9.3. If we need to estimate the parameter, and we have p hat, which is a demoted value of p, then we're using z again, and section 9.4. We do not have time to cover the variance and standard deviation. It's quite entertaining, but we're not going to have time to cover it. We have this idea called p-values. Yes, I will talk about them. They are important, but for many of you not using a TI-84, etc., p-values may not be all that helpful to you, but we will present them. They work okay with the z distribution. They just don't work at all with the t distribution unless you have technology. Then it works every time. So here I talk to 2 different audiences. Are you using a graphing calculator? Do you have a working knowledge of it? Kind of late now if you haven't started yet. But if so, p-value will carry you the whole way, unless, of course, we happen to ask you for the value of t or z, which we always have the right to do, so you should at least know where to find it. Anyway, this idea of the probability p-value, if the null hypothesis is true, so HO is true, of obtaining a sample statistic with a value as extreme or more extreme than the one determined from the sample data. Now, that's a lot of words. I've had a little trouble understanding it, and this is a cleaner way than our book has to say about it. But the way I look about the p-value is it's like levels of rarity levels. How rare is this? Is it going to happen like once every 10,000 times? Is going to happen 30% of the time? 30% is not rare at all. 1 in every 10,000 times is quite rare. And then as you compare that number to alpha, you can make a decision. We'll come up with that in just a minute. So we take our level of rarity, compare it to the standard alpha, which is so often 0.05. And if we can get it to happen less than 5% of the time, that's considered rare, and that usually invalidates HO. And we'll have much more to say about that as I just previewed briefly what we're going to talk about. So we have 3 kinds of hypotheses tests. One that corresponds to the left tail, one that corresponds to the right tail, and one that corresponds to both tails. So, of course, for H1, HA, this is the less than, this is the greater than, and of course, this is the not equal to. So that's basically all there is to it. HO is sitting in the background. In more advanced work, HO is rarely even mentioned. You just talk about H1 because it's got all the information in it. The parameters stay the same, the value stays the same, and HO just gets the equal sign. That's the way it's done nowadays, at least. Some of these books don't seem to catch that yet. But anyway, H1 is what controls it, as we said in the past. So the type of test depends on the region of sampling distribution that favors rejection of HO. That's H1, in other words. So this region is indicated by the alternative hypothesis H1, HA. And so here's our left tail test. The alternative hypothesis, HA in this case, contains the less than inequality symbol. Here it is, right there. It's less than some number k. And if, as they're going to say in a little while, if it falls into this darker zone, this critical region, we're so critical that we do not like HO anymore. We will pick HA as our favorite hypothesis, H1, each way. Does not matter. However, if we don't have that kind of evidence, HO is the winner, and it always gets the lion's share of the territory. It's assumed to be true. We need to really force the issue to prove that it's wrong. So that's just the way the game is played. So HO has to get at least 90% of the curve. Okay, if we have a greater than, and this, of course, this HO can always be replaced with an equal sign. I'll just make sure you get that. You may go to the other one if you want, but if you get a mistake, then I'm afraid I'll be very tempted to charge you a point, which I don't want to do. Anyway, we're headed towards the right, and we find values that are extreme enough, then we can, as I say it another way, reject HO. In other words, we prefer HA. HA is our favorite hypothesis. I'll just circle it. But if we can't get far enough, we're going to keep HO. Don't reject it, or if you want to fail to reject it, there's even a fail to reject. Let's not go there. Don't reject HO. In fact, it is our favorite. We can prefer HO. If you just want to say it more directly, I have no problem with that. Most people I know that teach stats don't like to say it that way. There is a kind of a legalistic notion here that we have to be careful with, but as long as you don't use the word except, you should be okay. So you may say it a little bit more formally by don't rejecting HO or fail to reject HO, or you may say it a little lighter and just prefer HO. And when we ask you to comment on these things, then this is the type of thing you need to put into words. Basically, a comment is just kind of rephrasing the math into English. Okay, with the two-tailed test, which you can see here, there's universal acceptance in the hypotheses there. Either mu is equal to a number or not equal to a number. The way it's not equal to it is either too large or too small. So if you have some sort of p, or maybe alpha, you could then cut it in half and then find the particular value for that. With z, it looks an awful lot like a confidence interval, because here's a hint. Only with two-tailed tests, this is very much like a confidence interval on the inside. So if you find that it lands in the confidence interval, guess what? HO is your favorite hypothesis. You're confident in HO. But if it doesn't, then HA, if it's too large, it goes over there. You prefer HA also if it's too small, outside of the interval of confidence. So notice I'm just putting down what you prefer right now, not addressing it more formally. Feel free to get as formal as you wish. For each claim, state HO and HA in words and in symbols. If I could just I can't get rid of this bar on top there, finally. Okay, so each claim state HO and HA in words and symbols. Then determine whether the hypothesis test is left, right, or two-tailed test, and sketch a sampling distribution and shade the area for the p-value. And yes, of course, I always like sketches. Confidence intervals, there's no need, but when it comes to hypothesis testing, I found that most A students tend to give me the sketch even if I don't ask for it. Now, we'll see if there's availability on that. We're going to work on that for the final. We're still working on stuff. But if it is possible to do a sketch, certainly appreciate it. Anyway, we talked about this already. They publicize the proportion of students at the school that are involved in certain extracurricular activities is 61%. And so in symbols, we just simply say that P is equal to 0.61. And yes, in words, it's 61%. In the dialogue in HO, the way is just to put it in decimal. But at least one that are involved is not 61%. So the not was a two-tailed test. Now, notice this at least one here did not refer to the question. It didn't refer to the question, so we can basically ignore it. That was just the subject. The thing they needed to talk about was at least one extracurricular activity, and that's fine. So that's 1, 2, 3, 4, 5. As you know, at least means at a minimum 1 and on up. But 61% is either true for HO or not true for HA, H1. So because HA contains the not equal to symbol, this is a two-tailed test. Okay, here's another one, and same instructions apply. Here the car dealership announces that the mean time for an oil change is less than 15 minutes. These are examples we saw already. So HO, let's just say the mean is equal to 15 minutes. And then we did say it was less than, so this is a left-tailed test. Remember, HA is the controlling hypothesis, H1 if you prefer. And so it's a left-tail hypothesis test as stated earlier. And you could always pause this. If I'm going too fast for you, feel free to pause the show. State hypotheses, determine what type of test it is, and let's see, the company here advertises the mean life of the furnaces is more than 18 years. This is getting repetitive. And so here the mean is either equal to 18, and the units are up to you. We don't generally worry about them. And here, if it's more than 18, then mu is greater than 18. And it contains the greater than symbol. It's a right tail test. And we reject HO, just to say it in a more formal way, when it gets to be too large. And we don't reject HO or fail to reject HO if it's smaller or even somehow less than. So it does happen. Then maybe it's only 16 years, and so you'd be over here. So of course you'd want to keep HO. But the claim is that they're actually doing quite much better than they thought they had been doing. Okay, so decision rule. Let's see, if P is less than alpha, then reject HO. If P is greater than alpha, then fail to reject HO. In other words, HA is our favorite hypothesis. And here, of course, HO is our favorite hypothesis. So if we can show rarity, it's less than some standard level. For example, the p-value is less than 0.05 as an example. We get like p equals 0.04. It's going to happen 4% of the time on its own due to random chance. 4% is less than the standard 5%. Yeah, so we would have to reject HO. That is HA, I'm sorry, failed to reject. I had that backwards. And that would be failed to reject HO. We like HO, and HA, H1, whichever you prefer. Okay, and then we have a way of saying claims. I do not worry about this in particular. However, some of you are ambitious. Maybe you've had a little experience with this in the past. Feel free to use these type of things. I simply don't really worry about this, though. But if you think you might be doing a little bit more of this in the future, then it would be a good idea to get into this. This is almost another branch of statistics that can take quite a bit of weaving through. Good for contracts. I actually worked for a contracts department briefly, and that was quite an experience. So let's go to section 9.2, and this time we have hypothesis testing for the mean with sigma known. So yes, we're able to use Z, and we'll talk about how hypothesis testing works from beginning to end. So we find p-values, how to use p-values for a z-test, and then the focus will be critical values. In other words, z versus z, or maybe t versus t. We'll see how that works, and p-values can be safely ignored if you wish. How to use rejection regions for a z-test for a mean when sigma is known. Okay, so here the p-value is found to equal 0.0237. It's going to happen. This extreme event will happen about 2% of the time on its own due to random chance, but only about 2.37% of the time due to random chance. So if your alpha is 0.05, this is rare. 0.0237 is less than 0.05. I call it rare. Some books call it significant. And that means you will reject HO, you will like HA. HO doesn't like rarity. HO likes to be the status quo. So it depends how you want to say it. Reject HO is the formal way. If you want to just prefer HA, I'll just say pref, and that would be fine. Let's take a look at another example. Yeah, we just said that. Okay, what if alpha is 0.01? This is the strict one, and this is a gray area type of problem. These are good problems. Here, when this item that we have found is going to happen and be extreme, more extreme than what we found, 2.37% of the time, that's actually greater than the 1% it's being held to. That's a different conclusion altogether. And it is greater than 0.01. You fail to reject HO. You like HO. This is not considered rare. Not rare enough anyway. We did have a strict standard. And it is two separate problems. Here we have a strict scenario, and it wasn't able to get underneath the bar, so to speak. HO is chosen. You fail to reject it. That means you basically prefer it. It's not rare enough to be rejected. So HO wins. After determining the hypothesis test standardized test statistics, such as Z or T, and the test statistics corresponding area, do one of the following to find the p-value. For left tail test, p is equal to the area in the left tail. For right tail test, p is equal to the area in the right tail. Fill that in here. Yeah, screwed it up there. Okay, then for two tail test, p is equal to 2 times the area in the tail of standard statistics. So pick a tail and double it. In other words, my rule of thumb is if you have to use p-value and you're not getting it from a calculator, then what you'd find in a table, you'd have to multiply by the number of tails you have. Left and right have 1 tail each. You leave the number alone. If you have a 2-tail test, you must double it. This is a disadvantage with using p-values. This is not many people's liking, but anyway, let's take a look at what happens for a p-value with a left tail test, a test statistic of z equals 2.23. So let's put in a few of the missing items here. And alpha is held to a very low 0.01. Luckily, though, this is directly from the tables. That is one advantage with p-values. It's so easy to get, especially with z. So when you look for the z value of 2.23, and this is negative 2.23, I'm sorry. So yes, there's a negative here. The area to the left from the table, or even from your calculator, is pretty close to alpha, but notice it's going to happen 1.29% of the time on its own due to random chance. We had to hold it to exactly 1%. It didn't quite get there. Okay, anyway, p is equal to the area in the left tail. Z equals minus 2.23. That value is, as we'll see in just a moment, greater than 0.01. Similar to before, not rare enough. HO gets the win. It's rare, but not quite rare enough. Alpha is strict here. Find the p-value for a 2-tailed hypothesis test with a test statistic of z equals, and one could say plus or minus on this one. Decide whether to reject HO when the level of significance alpha is 0.05. For a 2-tailed test, p will equal twice the area in the tail of a standard test statistic. So you can pick either one. I usually go for the left one. It's just a little bit easier. So I'll just pick this one. So we look at minus 2.14, and we find the probability directly from the table. It's a left-facing table. Why not use the left tail if you have to do it this way? We find that one of those tails has around 1.6% in it. But then, mirror image with this 2-tailed test, there's another one over here. Let's not forget about it. So it's easiest just to double it. Multiply by 2, and you get 0.0324. So they took the hard route. They went to get the right tail, so they had to subtract it from 1. There wasn't any need. If you went straight to the left tail, just remember that minus sign, of course. Remember, you're looking for a small value. Your probability is already 90%. You've done it wrong. You've got to look for these tiny tail values typically in these types of problems. So we just said that p is equal to 2 times the single tail, equaling 3% total. And we didn't have an alpha, or did we? I don't remember. Alpha was 0.05. So yeah, this one is rare enough. It's less than the more moderate, the more typical alpha 0.05. So this is what I call rare or significant. That means that HO is rejected. It's considered too rare for the status quo to stand up to it. So HA is our preferred hypothesis. So it's different. I'll just go ahead and summarize that. It's the not equal to whatever the parameter was. So because we just said this, 0.0324 is less than 0.05, reject HO. And now we have a formula. Your book does talk about, it doesn't get used too much, but it's exactly the same as before. Z is equal to x bar minus mu. It's divided by sigma over square root of n. Sigma is known. So that's the standardized test statistic, Z. Sample's random, of course. It isn't cherry-picked. That would not be fair. At least one is true. Either it's normal or n is greater than or equal to 30. Your book makes a big production, wasting several pages on all that. But you don't have to worry about it. Either we use the word normal or you have a big N. sometimes even both. And recall that sigma over square root of n is also known as the standard error of the mean. So here's a step-by-step process. Verify that sigma is known, otherwise you'd be using t in a different section. That's the next lecture. And we have normal or n greater than or equal to 30. State the claim mathematically and verbally. At least state it mathematically. Identify HO and HA, or if you like H1, feel free. That does not matter to me at all. Specify the level of significance. In other words, identify what alpha is. It's usually one of 3 different values. Your book sometimes uses a couple of other ones. The only ones I would ever use are the big 3 that we mentioned earlier. So find that standardized test statistic. Yes, that often is done by hand. And just we go ahead and find that. The x bar, the mu, the sigma, the n is all given. It should be very easy. And find the area that corresponds to z. And use the table. Use the z table. It does not pertain to this particular situation. So find that area. Left, it's easy. Right, subtract it from 1. If it's two-tailed, be sure to double it. That would give you your p-value. Remember, p-value to me is unnecessary, so you do not actually have to use the p-value. I'm never going to ask a question that insists on the p-value. I'm a critical value man. I like the critical values because it works with t, irrespective of your level of technology. And since we'll be using t often enough, we still have a couple more sections of t. A lot of people find they get confused by the p-value, and yeah, that's not going to help you unless you have technology. So I'm going to be emphasizing the critical value. So as soon as we get through this p-value stuff, we'll see what the critical value method is all about. So this reviews what we did before. For left tail test, it's equal to the area in the right tail, left tail, etc. Sometimes you have to do 1 minus left to use the table, so you just have to remember that for the table if you're using the table. And for a two-tail test, remember to double the area in a tail there. So let's move on. Make a decision to reject or fail to reject the null hypothesis. So if P is less than alpha, it's considered rare, and HO doesn't like it. HO likes commonness and wants the status quo. So otherwise, fail to reject or simply don't reject HO. Accepting HO is kind of not a good way to say it, but I will go ahead and compromise by saying you may prefer HO. That takes a little while to sink in. I don't expect you to get it right away, but you need to get it though, because they do have a legalistic way of saying it, and I have a more of a, I don't know, easy to understand style, I hope. Interpret the decision on the context of the original claim, so be prepared to comment. We don't always ask you to comment, but you should be able to phrase what you've done in words. After all, somebody wanted to know the answer to this, and they need you to know what you're doing. So you need to kind of put what you've done. Even if you made a mistake, a comment will, maybe it'll enlighten you and say, oh, this is not possible. Maybe I need to start over, or at least you get partial credit for interpreting whatever you have. Okay, here's another example, and we'll still have some p-values to go. In auto racing, a pit stop is where a racing vehicle stops for new tires, fuel, repairs, and other mechanical adjustments. The efficiency of a pit crew that makes the adjustments can affect the outcome of a race. So anyway, a pit crew claims its mean pit stop time for the new tires and the fuel is less than 13 seconds. A random sample of 32, notice that's greater than 30. We don't need normal here. It has a sample mean of 12.9. That looks awfully close, doesn't it? It's off by 1/10 of a second. But look at the standard deviation. It's 0.19 of a second. And then we even have a small alpha to go with that. Is there enough evidence to support the claim that at alpha 0.01? So it has to be, alpha 0.01 is a strict one here. Okay, so because we know sigma, and it's equal to 0.19, the sample is random, and it's equal to 32, it's greater than 30, and yes, we get to use z here, fortunately. And so the claim is that the mean pit stop time is less than 13 seconds. The less than sign goes with the alternative hypothesis. We're talking means here. Should be a colon there. And then, by default, you may say that mu is equal to, or if you want to say greater than, that's your choice. If you want to put it in the other terms, if that helps you, go ahead and use it. But all you have to do in my class is to say equals 13, because everybody's focused on HA. And that's where it says less than 13. And that's also the claim, which is pretty typical. So the level of significance is as follows. Z will equal x bar minus mu divided by sigma over square root of n. So x bar was 12, mu was 13. That comes from the hypotheses, by the way. That's what they're suggesting in the claim. The number relative to what we're talking about is 13. So that's what mu happens to be. Now the standard deviation is 0.19, and we have 12 minus 13. Was that 12.9? Yeah, it's 12.9 for x bar. Yeah, so we got a number pretty close to 13, 12.9 minus 13. So we can continue, and we will assume, of course, that mu is equal to 13. Kind of go with HO until we prove otherwise. So we're kind of assuming that HO is true, even though it may or may not work out to be true according to our evidence. So use a table and find the area corresponding to Z equals 2.98. When you look it up, you see it's quite rare. That number is way less than 0.01. What we found is a very rare event that would happen about 1 in 1,000 times, or 14 times in 10,000 times. That's real rare. If you want to put a few more decimals, you can compare apples to apples, go ahead, but it's still rare. That means HO is gone. It's out of there. And so the p-value equal to the area to the left is really small, of 2.98, is quite tiny. This is not going to happen on its own very often. Something's up, in other words. This is not going to really happen randomly much. Hardly ever. One out of every 1,000 times approximately. We're not going to go with that. We're going to go with the 999 times out of 1,000, to be honest. That's kind of the thinking behind all this. And because the value is less than alpha being 0.01, you reject the null hypothesis. You like HA, and HA was saying that, yeah, it's less. It's a less than type of a test, so that's what we have. Let's go to another example. I guess this is probably it for p-values. According to a study of U.S. homes that use heating equipment, the mean indoor temperature at night during winter is 68.3 degrees Fahrenheit. Mine's quite a bit lower than that, but that's just me. You think this information is incorrect, and you pick 25, only 25 homes that use heating equipment in the winter and find the mean indoor temperature is 67.2 degrees Fahrenheit. So from fast studies, the population, notice that sigma is 3.5, and it's known to be 3.5, and yes, because 25 is less than 30, we did need to see that word normal, or we'd have to shut it down. And we're not going to be doing that here, except in the occasional weird web work problem. You're not going to really be shutting these down. So is there enough evidence to support our claim that it's incorrect when alpha is equal to 0.05? And you may use either a z-value or a p-value. We'll talk about that in a little while. And notice there's no direction here. Where's Waldo? Where's the direction? Greater than? Less than? Don't read into things that aren't there. Yeah, we see the numbers lower. But does that mean it's less? No, it doesn't. We didn't say that. You said it's incorrect. And incorrect means a two-tailed test. That's the not equal to sign. In fact, one way of thinking about it is to just assume it's a two-tailed test until you see a direction. And if you don't see the direction, that means it isn't there. Lots of people just dive in and start throwing inequalities around when the not equal sign was actually more appropriate. It's kind of like playing a football game and suddenly, right in the middle of halftime, let's make it a soccer game instead. No, that's not going to happen. Okay, anyway, solution. Because sigma is known as 3.5 degrees Fahrenheit, we have a random sample, of course, normally distributed, of course, and yes, we can use z. A known sigma gets us to z, which is usually a good thing. Most people prefer z. It's a little bit easier to deal with. And the claim is the mean is different from 68.3 degrees Fahrenheit. So here, HO says the mean, of course, is just equal to 68.3 degrees Fahrenheit, and then HA, or H1, mu is not equal to. So it could be like 60 degrees or 75 degrees, like a pendulum wildly swinging out of control. It could miss it on both sides. Just because our sample is a little less doesn't really mean that much. Anyway, the level of significance was 0.05, as they said before, And we have, of course, our test statistic, in case they haven't given it to us, which they hardly ever do. We do have to calculate x bar minus mu, and so we find that there's a difference of around 1 degree in the negative direction. And we divide by standard error, and eventually, without any details, to 2 decimal places. Remember, 2 decimals. A lot of people forget that on tests. If you're using a table, it makes no sense to give me anything but 2 decimals for z. And we assume, of course, that the mu is equal to 68.3. They just said that in HO. HO just said that, so we're going to assume this is true. We give HO the benefit of the doubt until the cards are stacked against it like last time. Let's see what happens this time. This time, the area corresponding to 1.57, and it's a two-tailed test, so we did have to double. We had to take something times 2. I won't tell you what that is, but as we doubled it, we get 0.0582, close to 6%. That's not rare. Why do I say that? Because it's greater than 0.05, which is our particular alpha here. So we get something that on its own will happen 6% of the time. That is to be, less than greater, that is not equal to a certain number. Well, this number isn't considered to be rare. It's close call. I love close calls. I've made them razor thin in the past. I don't plan to do that this time. And sometimes you don't have a close call at all, and sometimes you do. And this is another close call. So we had to double the area to the left, and using the left version is the easiest one, because if you're using a table, the left is much easier than the right side. You don't have to worry about complements at all, but you do have to double it. So I'm kind of sick of p-values personally. I can't wait to get to critical values, so let's get to that pretty much right away. Oh, actually, we have not multiplied by 2. I take back what I said. As you double the 0.0582, it's not even a close call at all. Now we're up to 11.64. So silly me, I forgot my lines. We've got about 6% in each tail. So as we double it, we're up to almost 12%, 0.1164, which is way bigger than 0.05. So yeah, so multiply by 2, and you get nearly 12%. That's going to happen about 12% of the time on its own. That's not rare at all. Even 0.10 doesn't say that's rare. And 0.10 is kind of a looser standard. So we doubled it, and we got equal to that number, 0.1164, greater than 0.05. We failed to reject null hypothesis. In other words, HO is the winner. We don't reject it, so we do prefer it. So winner, loser, kind of like a sports umpire, referee. Not enough evidence at the 5% level of significance to support the claim that the mean indoor temperature at night during winter is different. So there's not enough evidence to say that it's different. So in other words, it's about the same as 68.3. So to say it directly, we could say that the mean temperature is about 68.3. It's kind of in that confidence interval. Two-tailed tests work for confidence intervals. Yes, there are one-tailed confidence intervals, but they are beyond the scope of this class, and we elect not to talk about them. But when it comes to two-tails, sometimes I do like to bring up the overlap between the two subjects. I wish we had time for more time to exploit that, but we just don't have it. Now, of course, here we have the TI-84 Plus that can help you. We want to get to the z-test by inputting data stats, and then you have the various items here. And so there's a little bit of missing information here, but we do have some stuff there. So anyway, the version I looked at before, none of these were missing, so I'm not sure what happened. But anyway, if you're using a TI-84, it's also done in the book as well. But the p-value, if you're using a calculator, shows up here in a particular other example. This one is not the same example as we have. And notice how many decimals there are. Yeah, in the business math class I've been teaching, we've been using 10 decimals there. So if some of you are just using 2 decimals, shame on you. You should be using more, but at least 5 decimals, I guess. But calculator will give you plenty, and it is less than 0.05, reject null hypothesis in this example. They really didn't talk about particularly. So rejection region is the range of values for which HO is not probable. We reject HO. In other words, let's say we have a two-tailed test. The rejection region is like the critical region. It's the dark side, where HA is our winner, because we've rejected the status quo. Lands in either one of those dark regions. That's the rejection region. Rejecting, of course, HO. Rejecting HO. It's an HO world, which I kind of disagree with personally, but that's just the way it is. So if a standardized test statistic falls in this region, the null hypothesis is rejected. Now we're going to be using critical values and by and large bypassing p-values from here on in. So we're pretty much done with the p-values. And as I say, primarily because the t-distribution is not p-value friendly at all, unless you have technology. So because at least half of you are using the table. And that's what I assume. I assume you're using the table unless you tell me otherwise. Give me calculator steps. Otherwise, I think you're using a table. And some teachers, some students thought that I understood they're using a calculator. And I don't understand that. I assume you're using a table until you show me calculator steps. And that's how I know the difference. Otherwise, you're going into the wrong crowd and you'll be graded on a different type of scale. A critical value Z0 or ZC, or just plain Z if you wish, separates the rejection region from the non-rejection region. So this could be a Z0, kind of a borderline number that separates the two. And by the way, if it falls in the regions rejected, yeah, we just said that, okay. And now, finding critical values in a normal distribution. Specify the level of significance. So, that's your 0.05, 0.01, 0.10, and this is for your alpha. Decide whether it's left, right, or two-tailed, of course. Find the critical values. A lot of these will look a lot like the confidence intervals. So we'll see some familiarity there. When the hypothesis test is left tail, find the z-score corresponds to a value of alpha. Right tail, find the z-score corresponds to an area of 1 minus alpha. This is just like reading the table. And two tail, well, then basically you take alpha over 2. And I'd go for the left one and just put a plus and minus sign on it. That's what I would do. I do the left one. It's just easier. So if you have alpha 0.10, half of that is 0.05. And look that one up on the left side. Left is easier if you're a table user. And then just make them both plus and minus. So here are some pictures, left, right, and two-tailed test. You should sketch the normal curve. Doesn't have to be a work of art, but sketches go a long ways to explaining yourself, and I feel you understanding what's happening. So if you understand enough to make a sketch, that's half the battle at least. If you really don't know what's going on and a sketch doesn't help you, then either you're some kind of a genius, which I have met, or you just think completely differently, or you really don't know what's going on, which is much, much more likely in my opinion. So based on my experience teaching stats for many, many years. So let's see, we've got the vertical line at each critical value. So notice the Z0s are basically the line in the sand, or lines in the sand for a two-tailed test, for which if you cross over to the dark side, you've chosen HA or H1 versus the status quo, which is in beige, and the dark side is HA, just to make it as simple as I possibly can. So find the critical value in rejection region for a left tail test with alpha being 0.01. That's the strict one. That value, which you may as well have handy, because you'll probably see this one again, is z equals minus 2.33. We did not see this with confidence intervals, but that one happens to be true. If you look up in the table, and the table value would be as close as you can get to 0.0100, may not be exact, but pick the closest one, or use your calculator and you'd find the 2 decimal places, that's your value of z. Z0 is a nice way to separate them out. You could say other things like z-test or z-critical value. I've used z-CV, critical value, that's a borderline value. Z0, more compact. Your book chooses not to use anything, unfortunately, which is sometimes confusing, and especially when I'm grading tests, it can get confusing as well. So any clarity you may give me is very helpful. So anyway, negative 2.33, so negative 2.33. Now let's take a look at alpha 0.05. This one will look familiar. It's a two-tailed test, so maybe, yeah, it will look familiar, because what we've done here, we're going to cut the alpha in half because it's two-tailed. They have to share equally on the left and the right, so you get 2.5% each. And as it turns out, when you look up 0.0250 in the table, you'll get a number. It's extremely close to negative 1.96. And just by symmetry, you can just stick the plus sign on the other one, where the two-tailed is always plus and minus, whatever the number is. Now, because we've got 95% in the middle, this should look familiar to you. This is the ultra-popular 95% confidence interval. Notice we have a two-tailed test. If we just reverse our focus and look on the inside, oh yeah, we did that one already. And the z's are the same. Z zeros, if you wish. So the area to the left of z0 is half alpha is equal to 0.025. And then if you choose to take the cumbersome, more complicated route, you could, if you want, take 1 minus that value to get to 0.975. If you wish, that would be the value that goes over here. And I think I did have a PowerPoint, which we didn't have a chance to show you this time. But that's also true, but I find that to be cumbersome. I just say if you find the left one and stick a plus sign on the one for the right, you're done. Good enough. And the calculator makes it even easier, of course. So anyway, you've got plus and minus 1.96 is very popular Z values. Also goes into play for the 95% confidence interval, extremely common. And this also could be thought of as a 5% level of confidence, two-tail. Same exact message. So critical values are minus and plus 1.96. So I'll just put equals or a colon there. So rejection regions are to the left of minus 1.96 and to the right of positive 1.96. Basically the same thing over repeated. Okay, decision rule. To use a rejection region to conduct hypothesis, and we're using the critical value method. Let's make sure we see this. The critical value method is quite versatile. May not have enough information, but the p-value has some extra information that talks about the level of rarity, such as 0.001, very rare, or 0.35, not rare at all. And different decisions are made based on the level of rarity. But here we've got the critical value, which is easier to do, but it doesn't have the extra information a p-value has. So, but if you're just looking to get the job done, and I don't even ask you for p-value ever, I can't guarantee about web work, but I will not personally ask you that. So in fact, if any of the written problems happen to show p-value and you'd rather just do critical value, you have my permission to do that. But anyway, if the standardized test statistic is in the rejection region, then you reject HO. It's an HO world. So yes, when they talk about rejection, they assume that you all understand it's HO. I don't quite see it that way. I think it's HO versus H1. Which one's the preferred hypothesis? That's the way I've always looked at it. And if it's not in the rejection region, that means you're basically accepting it and you fail to reject HO, you're preferring HO. So yeah, so if you look at the preferences, the positive side of things, if you're rejecting HO, then you must like H1. If you're failing to reject HO, then you are just accepting HO. Get rid of the double negative, and you're right back to preferring HO. So there's the pictures. Remember, the dark zone is where you reject HO, and HA is our winner, H1 is our winner. And failing to reject is tantamount to preferring or even accepting, but I really shouldn't use that word, the HO. So status quo always gets the lion's share of the room. For alpha 0.01, it gets 99% of the territory, so to speak. So here's a step-by-step process. Verify that sigma is known, or we wouldn't be in this section. Random sample, of course, and either it's normal or n is large. State the claim. We've gone through some of this before already. State the level of significance, so identify alpha. Yeah, that has to be given. Now, we've had open-ended problems where we'd let you pick the alpha, but that's just too much grading for me. So I'd rather just have one or two, not 4 or 5 grading keys. Determine the critical values, so use the table. And here, although we do have some overlaps of confidence intervals, pretty much you have to find it to get it. The other book has a little bit of a table. Maybe I'll supply that for you on another lesson here coming up. Determine the rejection regions, the dark zones. And then, of course, if they haven't given you the z, which they usually don't, z would equal x bar minus mu divided by sigma over square root of n. And if you'd like to call this sigma sub x bar, I guess you could do that if you prefer. And notice it did say sketch, didn't it? So yeah, I love sketches. Make a decision to reject or fail to reject the null hypothesis. So Z is rejectable, reject HO. Otherwise, don't reject it. Interpret the decision in the context of the original claim, or just to summarize what happened in English. Somebody may want to get to the summary, the executive abstract, in other words. So here's a good example. Employees at a construction and mining company claim the mean salary at the company's mechanical engineers is less than one of its competitors, which is $88,200. A random sample of only 20 of the company's mechanical engineers has a mean salary of $85,900. Assume that the population standard deviation is 9,000. I don't know how that got lost. And the population is normally distributed. That saves our 20. So we did have to see the word normal with a small sample size. Alpha is 0.05, the standard alpha. So because sigma is known, and actually it's 9,500, I take that back. The sample is random, and the population is normal, we can use the z-test. It's all z here. 9.3 will be t distribution. Otherwise, it's exactly the same. The claim is the mean salary is less than 88,200. So the claim is, or the mu is strictly less than the 88,200. And make it easy on yourself. Why don't we just say the mu is equal to 88,200? If you have to list HO, which I'm afraid you do, it's a beginning class, then just use equal. Make it easy on yourself. I tell you this, and I expect probably at least a third of you will forget about it and just stew about it and get it wrong or whatever. So I just try to help is all I'm trying to do. So if you're following the lectures, then you will take heed and save yourself some time and undoubtedly get a better score. Because the test is a left-tailed test, the level of significance is alpha equaling 0.05. Critical value is z equals 1.645, or if you prefer to use 1.65, you may. Our book mostly uses 2 decimals, but this is a little bit more precise. It just was pretty much exactly halfway, so some books do mention this. Okay, so it's a left-tail test. Rejection region will be one that is simply less than 1.645. So let's look and see what we got. Do they have a picture coming up? Yes, they do. So let's get to the picture in a minute. So z is equal to x minus mu divided by sigma over square root of n. And so we find the difference. Looks like that's about a $2,300 difference. So our numerator is minus 2,300. I don't happen to know what the standard error is. I don't have my calculator with me. And we assume, of course, that the mean was equal to 88,200. The big question is the 85,900 small enough, or is it just kind of random chance? That's the big question here. Is this just something that happens randomly? It doesn't really have much meaning? I mean, 2,300 is 2,300. I'd rather have it than not have it. Anybody would. But it may not be considered significant. And we look at the z, and the z does not look like anything that's going to matter very much. That's kind of not a very important z. And we did not beat the minus 1.645. A less than test means that z0, the critical value, ZCV if you wish, the line in the sand was minus 1.645. We wound up at only minus 1.08. That's where we wound up with our data. And that could be called Z data, by the way. That's the way I learned it, to keep the Z separate. Just call it Z if you wish. You call this Z critical value, just giving you other things to chew on. But keeping your Z separate, which your book does not do, is always helpful for your instructor as he tries to grade your test. So when you have the bottom 5%, that settles into a Z0 of minus 1.645, or even minus 1.65 if you want. The point is the 1.08, and the sketch is worth 1,000 words, is not in that rejection region. We did not cross over to the dark side. Yeah, it's less than average. Average would have been exactly 0. If we hit exactly what they expected, we'd get Z equals 0 because the mu's, be the same. But here's less, but it isn't less enough to matter. So that's why we do not have enough evidence at the 5% level of significance to support the claim that it is less than 8,800. So it's not enough evidence to say that it's less. In other words, we're thinking, looking back at HO, which is the winner here, we would have to say that HO, which we prefer, is saying that the mean is really about, I'd like to say approximately equal to, I think to be dramatic, I'll put the approximately equal to $88,200. It's approximately the same. So we don't have enough evidence to show enough difference. Notice we did not get a p-value. We could, but we didn't. So be sure you understand this decision making. This is quite important here. Circle the asterisk. Even though your sample is a mean of 85,900, you cannot, at the 5% level, support the claim that the mean is less. Cannot support the claim that the mean is less than 88,200. The difference between your statistic of 85,900, which is around $2,200. Let's see, what was the other one? 88,200. The difference, as we said, was about 2,300. That was not large enough. It looks large, but it isn't. It really isn't large enough. We have a big standard deviation and not that big a sample size, so we just didn't have enough evidence. It's probably due to sampling error, random chance, not rare enough to be remarkable. So HO gets all the close calls. And working as a statistician, we're almost always interested in HA. We're looking for new things to do, new ways of getting things done, and that's nearly always in HA. And when we just miss the call, like, our p-value is 0.051 and alpha is 0.050, those are very frustrating, but we had to be honest about it. We had to report our findings and bite the bullet and maybe try again another day. Okay, here's another example. A researcher claims that a mean annual cost of raising a child is, by married couple families, is over $14,000 a year. So random sample of these families, the average turned out to be $13,795, $795. That's a little less. Does that look like a lot? Well, here's the difference. We have a huge sample. That tends to magnify the differences. When you have 20, you can get by with a kind of a large difference, but when you have 500, puts everything under a microscope. I have a hunch. I know which way this is going, but let's just keep going. You have a pretty big standard deviation, but alpha is kind of the loosest alpha of all, 10%. So we give HA, or H1, the biggest territory possible. So this one is not HO friendly. In other words, it's about as large as you ever see. Can we reject the claim that the mean is 14,000. I'm looking for a direction. I'm looking. I do not see any kind of direction. So it is claimed that, so there it is way up here. There's the claim that the mean is simply 14,500, or 050 rather. So this is going to be a not equal to type of scenario because we do not see a direction. I don't see greater. I don't see lesser. They're not there. By default, we have to pick not equal to. So you have to think about it a little longer. So because standard deviation is known and equal to that number, it's random. And yes, of course, n is large. So yes, once again, we're using z. So the claim is that the mean is 14,500 or 14,050. Strange number there. So we put that in HO. That's for the two-tailed test, very often HO gets the claim. And HA, H1 means that mean is simply not equal to 14,050. Could be higher, could be lower. What we found was lower, so we're mostly looking at the left end of things, but officially it is a two-tailed test. Almost like we're turning the confidence interval inside out in a way. It's one way of looking at it, only when you have a two-tailed test. So alpha 0.10, and turns out that if you look it up, you get 5% in each tail, alpha over 2. This is just like a 90% CI, analogous to a 90% CI. That's what's in the center here. And we've seen that one before. That was Z equaling minus 1.65 and plus 1.65. Here they're using 3 decimals. So the rejection regions are when you cross over to the dark side and you get less than the negative. So here's your negative 1.65. I'll just round it. And then here we have the other one, positive. And if it's greater than 1.65, it's also rejectable, goes into the dark side. Otherwise, you're in the confidence area and the confidence interval, and that's where HO wins. So let's fill in the details, which you probably have memorized by now. And so we take the 13,795 minus the 14,050 and divide by the standard error. And we assume, of course, that the mu is equal to the 14,000. And it turns out when all the dust settles, we get 1.98. And that's looking like it might do the trick. We did kind of set the line in the sand as 1.65, 1.645. And yes, our value has crossed over into the dark side, to use a Star Wars reference, kind of a lame one, I admit. But HA is our winner here. We have enough evidence to show that we've caused a difference. We look at that raw difference in the between, which didn't look like much. If you look at the numerator, which I always find it very helpful to calculate this stuff out. I always appreciate when students show extra work like that. Minus 210 doesn't look like that much. We were looking at 2,300 the other day, the other example. Now, 210 makes a difference. It has everything to do with the 500 in our sample. That carried a lot of weight. Carries a lot of weight. So pulls the Z over into the corner. We reject HO. That's the more formal way to say it. We're not going to want to keep that one around because we pulled it over. It's past the line in the sand, the left line, that is. It didn't happen to have anything to do much with the right side, but there is one on the right side as well. You shouldn't ignore it. It's there, just in case it happened to be above average. So we reject the null hypothesis. HA is our winner. And that said that we had the mu different than the number. That's the end of the slideshow. So, by the way, that number was 14,050. It's different. Our number was far enough over with that huge sample. So next time we'll go into the end of chapter 9. That's going to go for more of the same as 9.2. The only difference is sigma is not known, and we have to use S, which means we have to use T all the time, and all critical value method all the time too. If you want to use the p-value method, you may, but that means you would have technology. No doubt about it. And you would have to show me some calculator steps or tell me what you're doing. Otherwise, you're leaving me hanging, and I don't usually appreciate that. So be clear. If you're using the calculator, let me know. Once is enough. Calculator steps are always appreciated when it comes to using some of these tests. But anyway, we'll also get into proportions, which gets us back to Z. In Chapter 10, we've got 3 different versions of hypothesis testing. Lecture number 17 will be 10.1 and 10.3. Lecture 18 will be 10.5, and a final review. So as we clean up shop in 10.5, we'll also give you a final review and talk a little bit more about the final as things become more settled. It'll be more on Blackboard this time. And you can still send the homework. I'm looking at the homework now. Not the midterms are graded, and I grade the homework a little more loosely. If I give you a high score, it doesn't guarantee you are perfect. It just meant that you checked the boxes. I usually pick one tougher problem per chapter and make sure you did it. And I look for completeness and sketches, things like that, when required. And then I size it up and see how well you did on the homework. And so a score of 10 is the perfect score, and 9 and 8 are not bad. When you get down to a 7 or below, that means you really kind of messed up on something. But be sure you're turning that in, because that all contributes to your grade. Each one of the homeworks is 6% of your grade for a total of around 12%. So it does add up. People who do their homework are saying they want to pass the class, and those that forget the homework are pretty much telling me the opposite. But we know you're not in that situation at all. So anyway, have a nice day, and we'll talk to you later.